Hello students, welcome back to Math 332 Linear Algebra. So in the previous video, we have seen the concept of row space, column space, and null space, and the significance of all these spaces. So in this video, we are going to learn how to compute the dimensions of all these vector spaces. So as you recall, in order to compute the dimensions, we will have to first establish a basis for that particular vector space. So we are going to learn how to find a basis for the row space, the column space, and the null space. So how do we do that? Well, as I mentioned before in this course, basically the only computational tools that we know how to do is row reductions. So we're going to see and investigate what's the relationship between the row space and the column space and the null space of a matrix together with its row reduced echelon matrix. Okay, so without further delay, let's get right to it. All right, let's begin by looking at the objective for this video. So at the end of this video, you should know that the row space of A and the row space of the RREF of A, they are the same. That's true for the null space also. But the key thing is that the column space of A is not the same as the column space of the RREF of A. We'll look at it why this is true. And obviously, you need to know how to find a basis for the row space, column space, and the null space. And then you will be able to obtain the rank and the nullity of the matrix. So as you can see, there's a lot of things going on here that we have to know, okay? All right, a very quick review. If you have a matrix A of size m by n, so this is a notation for it. So these are known as the row vectors for this matrix. So these are the row vectors of the matrix. They are elements that is in Rn. And the row space of A is defined as a span of all these row vectors. There are m of them, but they are all in Rn. So these are actually from a subspace of Rm. So these are known as the row space of A. And obviously, you can take a look at the column vectors. So these are the column vectors. These are the column vectors for the matrix. So you have the column vectors for the matrix. These are vectors in Rm. So there are n of them, but they are vectors in Rm. So if you look at the linear combination of those column vectors, it will form a vector subspace of Rm. And these are known as the column space of the matrix A. The null space of a matrix is defined not by looking at the row and the column, but instead we are looking at a homogeneous system. You're looking at this particular system and collect all the solution for that system. So you're looking for all the x that is in Rn, all right, such that A multiply x give you the zero vectors. So these are also vector spaces. All these are vector spaces, null space, column space, and row space. So we can find a basis for all those vector spaces, and we can count the number of vectors in those bases. So that gives you the dimensions. So the dimensions of the null space of A is called the nullity of A, and this is denoted by this notation right here. And we'll see later on that the dimension of the row space of A and the dimension of the column space of A are the same. And the dimensions of the row space of A, the common dimensions of the row space of A and the column space of A is known as the rank of a matrix. So the rank of a matrix is nothing but the dimensions of the row space and the dimensions of the column space of the matrix. This two number is going to be the same. It's not obvious now why this is the case, but we will see it pretty soon in this video. To show you that we'll show you that the dimension for the row space of A and the column space of A are indeed the same. Okay. All right. So how do we find the dimension of the column space of A, row space of A, and the null space of A? Well, we know that already. We have to first find a basis. We need to find a basis for the column space of A, row space of A, and the null space of A. And then once you have a basis, you just have to count the number of vectors in the basis. All right. So the number of vectors in the basis, that's the definitions of the dimensions of those vector spaces. So how do we do that? Well, the only things that we know how to do is row reductions, right? So all the computations that we know how to do in linear algebra is setting up a system of equation and start to row reduce. So suppose you take a matrix and reduce it to this RREF. How do we get those informations of a basis of a row space, column space, and null space? By looking at the RREF matrix. Okay, so luckily we have this theorem here, these two theorems to help us. So this theorem 4.7.3 says that the elementary row operation would not change the null space of a matrix. So elementary row operation would not change the null space of a matrix. The next theorem says that the elementary row operation would not change the row space of a matrix. Well, this is perfect, right? This is great because now what it means is that when you do row operations to take matrix A and row reduces it to the RREF matrix, you are doing multiple elementary row operation, but every time you do row operations, you will not change the null space. Okay, so that means that the null space of A and the null space of the RREF of A is the same. And that also means that the row space of A and the row space of the RREF of A, they are also the same. So that's the very important implication of these two theorems. These two theorems shows you that the null space of A and the null space of the RREF of A is the same. Row space of A and the row space of the RREF of A is the same. You might wonder like why this will be helpful. We'll see in a minute that it's helpful. One of the things that you probably already know that is that the RREF matrix is very simple. It's way more simple than the original matrix A. Most of the time, in fact, all the time you can just eyeball your RREF matrix and you're able to tell which column are actually independent and which row are actually independent, okay? So we're going to make use of that. All right, let's look at this example and you know what I mean, right? So this is a matrix A. It's very difficult to see that whether or not this column vectors are independent, for example. It's also very difficult to see whether or not these row vectors are independent, all right? But if you manage to take this matrix A and row reduces it to the RREF matrix. So for example, you can see right here, this row vectors and this row vectors and this row vectors, they are linearly independent, right? And this obviously doesn't contribute anything. So you can immediately see that we have three independent row vectors. So this is the row vectors. You can see, if you want to, if the first time you can't really see it clearly, you can go through the definitions, put a K1 of these vectors, K2 of this row vectors, and K3 of this row vector, and set it equal to the 0 vectors. And you can immediately see, you have to give it a try if you don't see it. But once you give it a try, you will see that if you put K1 here, K2 here, and K3 here, and sum it equal to the 0 vector, you will see easily that K1 is 0, K2 is 0, K3 is 0. So that's the reason why I'm saying that by inspecting the row vectors of the RREF matrix, you can immediately see that these three row vectors are independent. And in fact, we know more. We know that we have a redundancy here. All right, so what is the row space of A? Well, row space of A, very kind of difficult to see from here. But because we know that the row space of A and the row space of the RREF of A is the same, and the row space of the RREF of A is clearly spanned by these three vectors, right? So we will be able to say that the row space of A also spanned by these three vectors. And that's what we are saying by theorem 7.4.7. And not only that, we already established the comment that I make just now that they are independent. So these vectors, all right, these vectors are independent and they span the row space of A. So we can take these vectors, right, these three vectors as vectors that form a basis for the row space of A, right? So again, if you look at the matrix A by itself, it's very difficult to obtain that information. But the theorem says that the row space of A and the row space of the RREF of A is the same. And inspecting the row space of the RREF of A, pretty easy to see that the row space is spanned by these three vectors and they are independent. So this actually form a basis for the row space of the RREF of A. But the row space of the RREF of A and the row space of A, they are the same. So we can immediately just investigate the RREF matrix. We know that these three vectors can actually be selected to form a basis for the row space of A. So even though we are looking at the RREF matrix, we are able to extract informations to get informations that is related to the row space of A. We can do that because of the theorem, okay? And now, once we have a basis, figure out the dimensions will be very straightforward. In fact, you just count the number of vectors in this basis, so 1, 2, and 3. So the dimension of the row space of A is 3. All right, so now we are going to look at why the null space of A and the null space of the RREF of A is the same. So before we do that, let's look at this particular example right here. All right, so this is a very simple system of equations, two equations with two unknowns. So we are asked to solve for the x and y. So if you remember in the very first day of class, one way to solve system of equation is to put them into the augmented matrix, and then we row reduce to the RREF matrix that is going to look something like this. So you will have something that's like this. And then you will take a look at this system of equation and say that this is x equals to 1, y equals to -1. And then we say that this is the solutions for this system. Now, at the time, you all just follow the instructions and you'll be like, oh, okay, this is a method to solve a system of linear equations. But do you pause and wonder that, in fact, this solution is a solution for this REF matrix. This solution is a solution for this particular system. It's not the solution for the systems. So why at the time we actually look at this reduced system and say that this reduced systems, whatever solution that we have here, is the solutions that we have here. All right. So this if you understand this argument here, you will see that why the elementary row operation would not change the null space of a matrix, because they are looking at actually a system that is easier than this. Their system is always to be 0. If you consider for null space, you always look at 0. But in fact, we have a more general situation here, which will demonstrate that elementary row operation would not change the solution for the system. And the solution for the system is going to be the same as the solution for the system. So one way to see this is to think of this linear system right here. And we kind of already see that this system, if they have a solution, the solution is already hidden right there in the x and y. Right? What I mean is that the solutions, as we already know, the solution is kind of already hidden right there. So this is your x equal to 1, your y equal to -1. This is your x equal to 1 and y equal to -1. So when you do row operation, for example, you multiply the second row by 2 and then you subtract this this equation right here. So what you are trying to do is to try to get rid of all these coefficients so that we get better numbers, right? So we try to get rid of the coefficients so that at the end we have like just the x and just the y. And when you do that, you will see that when you do this operation here, right? So when you do this operation here, which is you multiply 2 to the second equation and take the first equation and subtract the second equation, you will see that when you do that, your solutions right here, if you do the same operation here and do the same operation here, you will see that all the numbers right here, which are the solution for the system equation, is still unchanged. You multiply 2 to the second equation and you subtract, so you get something that looks like this. This is exactly what you get by looking at this system. And then you divide it by 5, so you get this. So all the answer right here is actually not change, even though you do operations. So the elementary row operations that you do is kind of like you are sculpturing, right? You take a big rock, the gem is already in the rock, and you kind of like just take the hammer and all that and zero away all this coefficient. You just try to reveal the gem, that is the diamond or whatever that is in the rock. So this kind of the diamond and all that in this analogy is like all this answer here. So all this row operation is just basically chip away all the rock so that you will reveal the answer. So while you are chipping away all the rock, the answer here will not be changing. So that's the reason why the solutions for the system here is the same as the solution for the system here. So that's the reason why the solution for the system here is the same as the solution for the system here. And this explains why that the elementary row operation would not change the solutions for the system. And that will indeed explain why the null space of A and the null space of the RREF of A, they are going to be the same. All right, so let's back to this example. If you need to find the null space of A, right? So that's your A. So what we need to do is to set AX equals to 0 and solve for X. And what we do is we do that, and then we will row reduce all the way to this matrix. So this is RREF of A, right? And X, and then equal to 0. So we know the answer is the same. So we look at this system, this augmented system, and these are the pivots. So we have the pivot variable x1, x2, and x3. As you can see, x4 and x5 here are the free variable, and you can rewrite your solution as a vector form, and you will see that all the solutions for AX equals to 0 can be expressed as a linear combination of these two vectors. In other words, that the null space of A, which is by the theorem, same as the null space of the REF of A, is nothing but span of these two vectors. Again, you can see easily that they are linearly independent. If you can see it, just follow the definitions, take K1 of these vectors, plus k2 of this vector and set it equal to 0 vectors. And you can see that your k2 has to be 0 because of this. And then you have to see that when this is gone, pick another number, you'll see that k1 has to be 0. So you have to do it if you don't see it. But you should be able to see that this is easy to see that they are linearly independent. If you can't see it easily, please make sure that you follow the definitions and see why I said that this is easily seen to be linearly independent. Therefore, we can choose these two vectors. We can make a collection of these two vectors as a basis for the null space of A. So the null space of A actually has a basis that has two vectors in it. So the dimensions of the null space of A is going to be 2. So the dimension for this particular null space is going to be 2, and so the nullity is 2. All right, so now you see that we have discussed the row space of A and null space of A, and we haven't talked about the column space yet. So the column space is a little bit tricky. The reason why it's tricky is because when we do row operations, we would not change the row space. But when we do row operations, we actually destroy the column space, right? Because when we do row operation, we do operation like this. So the column is like this. So it is not going to be doing well if you do row operation on the column, right? So the column will be destroyed. The column space will be different, in fact. So I want to show you why this is different. So let's look at the same matrix A. Let's look at this particular matrix A here. So they have 6 columns for this matrix. This is the original matrix A. So it's column 1, 2, all the way to 6. We use the notation C for this column for vector A, matrix A. And let's look at the RREF matrix. So let's look at the RREF matrix. Now, so the RREF matrix have all these columns, D1 all the way to D6. Now, it is tempting to say, based on what we have learned from before, we're tempting to say that, hey, look, this column here, and this column here seems to be linearly independent. So the rest are redundant. So this one here, we can get this vector easily by combining column 1 and 2. So you can see these are like linearly independent. So maybe, so if you look at this one right here, so maybe we can say that the column space of A is actually spanned, right, by these 3 vectors, D1 vectors, D2 vectors, and D4 vectors. It's tempting to say that, but you can see, hopefully, you can see that if you actually do this, this is actually column space of J. All right, so I don't want to claim that yet. Just take a look at this particular span, the span of these 3 vectors right here, the span of all these 3 column vectors. Okay, can you claim that this is the same as the column space of A? All right, that's my questions. Do you see that this is actually a column space of A or not? Do you see that the span of these 3 vectors, can you say that this is a column space of A? That's my questions. All right, I would like you to pause the video, and I'm going to give you a moment to think about this problem. And when you think that you already have the solutions, you can restart the video and we will compare our solutions together, okay? All right, welcome back. And I hope that you have answer for these questions. And the answer is no. So one very easy way to see it is that look at this vector here. This column vector is 1, 0, 4, 1. Is obviously an element in the column space of A, and the span of D1, D2, and D4, which is the span of these 3 vectors, you look at all the possible linear combination of these 3 vectors, you can see that there's no way that you can reach the vector 1, 0, 4, 1 by simply looking at the linear combination of these 3 vectors, because no matter how you linearly combine these 3 vectors, this 4th component right here is always going to be 0, but this one right here is a 1. So there's just no way to get this vector. So you have a vector that's in column space of A, but it's not in the spans. So the column space of A, right, and the span of all these 3 vectors right here, they are actually different. Okay, they're actually different. Right, so because of that, we can see that the column space of A and the column space of this REF matrix of A, which is what we call J here, is actually not the same. So this is different. So for the row space, so the row space of A, right? And the row space of the RREF of A is the same. The null space of A and the null space of the RREF matrix is the same, but not for the column space. Not for the column space. However, the REF matrix, our matrix J here, still able to give us some kind of information. Now, the REF matrix is always a matrix as easier in the sense that because it's like it's already in a reduced form, and you can kind of like see a lot of relationship pretty easily. You can identify a lot of relationship pretty easily from this REF matrix. So, for example, you look at the column vectors D1, D2, and D4. Okay. All right, the vectors D1, D2, and D4 is clearly linearly independent. This is very easy to see that they are clearly linearly independent. That's the first thing that we observe. Also, we can see that D3 is related to D1 and D2 this way. D5 is related to D1, D2, and D4 this way. And D6 is related to D1, D2, and D4 this way. For example, now, so for example, as you can see, your D3 is this vectors 3, 1, 3, negative 1, 0, 0. Obviously, it can be written like this. Okay, D5 is this, so it can be written as 2 of this, minus 1 of this, and plus 1 of this. It's very easy to see it from our matrix J. All right, and so with the example D6 that I didn't write it down here. So because the REF matrix is a simplified row-reduced echelon form matrix, so the this kind of relationship you can identify just by a quick visual inspections. Now, what is special? What is special? This is going to be a little bit interesting. Is that I am claiming all the relationships that you observe from the matrix J hold for the matrix A. For example, that's what I'm saying. For example, I'm claiming. So I'm claiming because D1, D2, and D4, they are linearly independent. All right, so I'm claiming D1, D2, and D4, they are linearly independent. We have seen it just now. I'm claiming now the corresponding column vectors for A, which is our C1, C2, and C4, will be also linearly independent. Now, D1, D2, and D4 are linearly independent. You can see it by just a simple visual inspection. C1, C2, and C4, they are linearly independent. It's not obvious, right? It's not obvious at all. All right, you can take a look. D1, D2, and D4, they are linearly independent. It's very straightforward. Visual inspection, you can see that. I'm claiming that C1, C2, and C4 will also be linearly independent, but it's not so clear by visual inspection. You have to follow the definitions, multiply K1 to this, and multiply K2 to this, and set it equal to 0. And then if you solve for the K1 and K2 and K3 by definitions, you will see that the K1, K2, and K3, after you do the computation, will be 0. Okay, not only that, remember all the D3, D5, and D6 has this property, has this relationship. I'm claiming the corresponding C3, C5, and C6, the corresponding vectors C3, C5, and C6 also have exactly that same relationship. So you basically just change all the D to C. They are also related in exactly the same way. For example, all right, so let me write this thing down. So D3 is very obviously, you can see by just visual inspection, is 3D1 minus D2. Now C3 also have that same property, C times 3, 1 minus C2. It's not so obvious, but if you check, all the computation works out. So not only for that, all this relationship that we have for D will also carry for C. So we'll explain why we have this property in the future, right? But right now, just observe that we have this very strange property between the columns, the relationship between the columns of the RREF matrix and the columns of the the matrix A. So even though their column space are not the same, but the relationship between the columns in matrix J and the relationship between the columns for matrix A are the same. This is actually very interesting. All right, what's the implication of all these observations? Now, the implication is, so if you look at the RREF matrix, our matrix J, so we know that the entire column space of J is spanned by these 3 vectors and these 3 vectors only, because the rest of the 3 vectors is a linear combination of D1, D2, and D4. Also, by just visual inspection, we know that these 3 vectors are independent. Therefore, the basis, a basis that we can choose, right, for the column space of A is this. All right, it's D1, D2, and D4. So the basis for the matrix J, the column space of matrix J is this. However, everything that we see in terms of relationship between all these column vectors for the REF matrix J is the same as the relationship between the column vectors for the matrix A. So we can do this. We can say that, okay, the column space of A is spanned by the column vectors C1, the column vectors C2, and the column vectors C4. They are independent because D1, D2, D4 independent. So C1, C2, C4 is also independent. And you can see that all this relationship also holds, so everything is okay. And therefore, we can choose a basis for the column space of A as C1, C2, C4. So that is to say that the way we find the column space of A, the basis for the column space of A, is that we still do the row reduction. We do the row reduction and we get to this REF matrix. So we identify here, this one here, this one here, this one here form a basis. So we will look at the corresponding matrix, look at the corresponding columns for the matrix A. So this one right here, this one right here, this one right here will be a basis. So we don't say that these three are the basis for column space of A. We don't say that. We don't say that the column space of A, the basis is D1, D2, D4. But we look at the corresponding columns. Okay, we look at the corresponding columns for the matrix A. Then we say that those columns will form a basis. So that is how we utilize this relationship. All right, so let me review really quickly, okay? I want to illustrate the difference between finding the column space of A and finding the row space of A. So if you want to find the row space of A, you take this matrix A and you row reduce to this REF matrix, and you say this one here, this one here, this one here, these three rows form a basis for the row space of A. All right? All right. But you do not say this one here, this one here, this one here form a basis for the column space of A. You don't say that. You will say that this one here, and this one here form a basis for the column space of A. So we still make use of this matrix, but we'll have to look at the corresponding column vectors from the matrix A. So that's the difference between finding a basis for the row space of A, which everything will be looking at the REF matrix right here. But looking for the column space of A, we were not looking at the REF matrix. We just use this as a proxy, and then we look at the corresponding column vectors that is actually on A. Okay? All right, so the next question we want to look at is the dimensions, right? The dimensions of the column space of A, right? And the dimensions of the row space of A. Okay, so now we know that if you take this matrix A, row reduced to this REF matrix, so we are counting this one right here, this one right here, and this one right here actually form a basis for the row space of A. So the row space of A, you look at the basis, it has 3 vectors in that basis, so the dimension of the row space of A is 3. All right, so the dimension of the column space of A, so this one here, this one here, this one here form a basis. So we look at this. So even though we are looking at the column vectors that is from A, but the number of vectors is the same as the number of vectors here. So if you just count the number of vectors in the basis, it is also 3. Okay, so this 2 is the same in this case. The question is it always the same? Well, you look at how we count the number of bases in the row space and the column space, you will see that they are going to be always the same, because basically we are counting the number of pivots that is in the REF matrix, right? This pivot here, this pivot here, this pivot here. So this gives you the number of row vectors in the basis, all right? And this one here gives you the number of column vectors that is in the basis of the column space of A. Let me say that again, right? So even though the vectors are supposed to be this one right here for the vectors that's form the basis for the column space of A, but we are not looking at this individual vectors. We don't care about it. We only care about the number of vectors. So if you only care about the number of vectors, all right, this is 1 vectors, 2 vectors, 3 vectors. That's how you get this 3 here. All right, so this one here, 1 vectors, 2 vectors, 3 vectors. That's how you get this here. And in both cases, we are basically counting the vectors that is in the pivots. So this is 1 vector, 2 vector, 3 vectors for the row space of A. And then this one is 1 vectors, 2 vectors, 3 vectors. That is for the number of vectors that's in the basis of the column space of A. And as you can see, we just count the pivots. We just count the pivot. So you can we can summarize it and saying that if you want to count the dimensions of the row space of A and the column space of A, you just count the number of pivots in the RREF matrix. Okay, so that gives you the dimensions of the row space of A and the dimensions of the column space of A, and you can see they're always the same. And because they're always the same, this dimension that's common to both vector space is known as the rank of this matrix A. That's known as the rank of this matrix A. Okay. All right, so everything that we discussed before, it can be summarized in this theorem. So it says the row space and the column space of a matrix A have the same dimensions, and that common dimensions is known as the rank of A, and that's the notations. And if you recall, the dimension of the null space of A is known as the nullity of A. Okay, it's known as the nullity of A. So now let's look at this particular question here. We have this matrix from before, but it is a good time for you to review all the things that we have just learned, and let's see what answer will you get for these particular questions here. Okay. All right, I will want to give you a moment to work on these problems. So you should pause the video and work on the problems. And when you are ready, you can restart the video, and I'll be here and we can look at the solutions together. Okay, we'll see you very, very soon. All right, welcome back. So how do we solve this problem? Well, first thing you do is to take this matrix and row reduces it to the RREF matrix. Okay, so we want to find the basis for the row space, column space, and the null space. So the row space, the basis for the row space, you can just have to select these three vectors. These three vectors will form a basis for the row space. And actually right here, so please do not take this as your basis for the column space of A, but you take this instead. So you take this. So these three column vectors will form a basis for the column space of A, as you can see right here. So this one here form a column, form a basis for the column space of A. All right, so we have that already. It's very easy once you get into the REF matrix. This one here, the REF matrix, these three vectors form a basis for the row space of A. All right, but then, okay, look at this, look at this, look at this, but then select this vector here, this column vectors here, this column vectors here, so that 3 will form a basis for the column space of A. So column space of A, look at here, row space of A, look at it right here. Okay, null space, well, for null space, we'll have to look for the solution for the system, right? So if you REF this matrix, the system, you get that. So free variable, look at this is pivot, pivot, pivot. So the free variable will be x4 and x5. This is a very important observation. So we're going to say a little bit more about that later. So pivot, 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 free variable, free variable. So once you have free variable, you have these two vectors right here, and these two vectors will form a basis for the null space of A. So we can kind of see, we can use the number of free variable. We can use the number of free variable. This is critical. We can use the number of free variable as a proxy for the dimensions, the null space of A. So the number of free variable right here is x4 and x5. So every free variable kind of like associated with one vector that's right in front of it. So this one right here, okay, you can select them as the basis for the null space of A. So we have two free variable. So the nullity of A will be 2. So we can use the number of free variable as a proxy for the number of vector in the basis of the null space of A. Okay, all right. So if they only care about the dimensions, that's easy. But if they also wanted to know what vectors that is in the basis, then you actually really have to produce all the specific vectors. So if they care about the vectors that is in the column space of A, then you really have to compute that. The vectors that is in the row space of A, then you really have to compute that. But if they only care about the dimensions, so obviously they are all 3. These are the rank of a matrix, and these are the nullity, number of 2. This is a nullity of the matrix A. All right, so let's look at this again. So if you look at the RREF matrix in terms of dimensions, if you want to look at dimension only, so if you want to look at only the dimension, that's easy. Look at the pivots. This gives you the rank. So this matrix is rank 3. right? So this matrix is rank 3, right? How about the nullity, right? So the nullity, okay, you use the number of free variable as a proxy. So this one right here, free variable, free variable. So this one is going to be 2. So in fact, all this add up together will be the number of columns. So this is what we are going to look at, okay, in the next video. This is called the rank nullity theorem. So for every matrix, the rank of A plus the nullity of A will equals to the number of columns. So if your matrix is of size m by n, then this will always be n. All right, this concludes the first part of our presentations. In fact, we are going to continue to look at all these concepts that we learned today in the next videos. Specifically, we are going to look at the theorem called the rank nullity theorem. And it's a very useful theorem in order to help us understand the solutions of the linear system AX equals to B. So we'll see you there soon. Okay, bye.